Okay, we want to continue now with our refraction unit. Now, within refraction, we can actually get something called partial or internal reflection. So this will be important for this chapter, but also when we get into quantum, some really strange things happen with light. Light is a very peculiar particle wave. It's got a duality, which we'll talk about a little bit later. So here's a kind of a strange picture. We're talking about partial reflection, and you've probably seen this before. So here's a picture I found online of a woman sitting in a car putting on her makeup. You can see through the glass and see the person's face, but you can also see the reflection of the trees off of the automobile glass. Same thing here is a picture of a building. You can see into the building, so you can actually see through. That's obviously the door's open, but you can see through the glass. But you can also see the reflection of the outside bouncing off the glass. So in this case, the glass is allowing some light to pass through, but it's also reflecting some of the light. And that's a very common experience. You go out to your car in the summertime, you can actually see reflection in the car window, but you can see into the car at the same time. Richard Feynman, a really interesting physicist in the mid-40s and beyond, figured out this really bizarre what light really is, and there's something called quantum electrodynamics. We have a very basic behavior of light in physics 1 and physics 2. We treat it like a wave, sometimes like a particle. Feynman treated it correctly and talked about some really bizarre behaviors of light. If you find some of the stuff interesting, he has a book called QED, which is really fascinating. But anyway, now a couple things that we need to understand. This will be important for partially this chapter, but really something later when we study quantum. We said before that when light hits a boundary, it can either reflect or it can refract, but it turns out it really can do both at the same time. So I've shown the thickness of the light to show the intensity or the brightness of light. So here we have a full beam of light hitting a surface, air to glass. As we just saw in the photograph a minute ago, some of that light is going to reflect off, and I've shown that reflecting at the angle of incidence, angle of reflection, obeying the laws we have. And you can see the intensity or the brightness has gotten less because some of the materials, some of the light has reflected off, but some light is carried through. And as we just saw, when light goes from air into glass, it's going to refract or bend towards the normal, and so we get that. The light's going to carry on. But when it arrives at the next boundary, the same thing can happen again. So it's going to go from air to glass. Maybe this is a window, for example. It's going to go air, glass, air. It's going to reflect and refract. On this boundary, it's also going to reflect, so some of that is going to reflect away, and that beam itself actually could reflect back or transmit through. So this process actually continues on and on. This beam that refracted through can also refract back out, and so in addition to reflecting, can also refract. And again, this can go on forever. So I'm trying to show you that when we think of light as reflecting or refracting, it's actually more complex. There's actually a sort of a domino effect of light. Every time it hits a boundary, it does a little bit of each. And the intensity or the brightness will change as a function of that. Now, this gets really bizarre, and I'm not going to get into this, but it turns out that how much light is reflected and refracted has this very peculiar percentage cycle. So, and we may discuss this a little bit later when we talk about thin films. The AP is big about thin films, and it's a pretty complex topic, but it lays its foundation understanding that when we go from one material into another, we get reflection and refraction, and a certain percentage of these waves or particles are being allowed to go through or bounce off. Now, part of this that's important is that the amount that bounces and the amount that refracts depends upon the angle, and this kind of makes sense. If I come in very steeply, remember it's always relative to a normal line. If I come in very steeply, it's kind of like throwing a rock at a pond. Well, if I throw the rock at a very small angle, I expect the rock to go through, but with light, most of it goes through, a little bit reflects. And again, like a rock on a pond, if I throw it at a very large angle relative to the normal, I would expect most of the time the rock to skip off. Here it's showing most of the light skips off the thicker band here, and some of the light refracts. So we always get reflection and refraction. The amounts depend upon the angles. The really bizarre part is that we sometimes treat light like a wave, and sometimes we treat it like a particle. And we'll get into this particle or photon theory of light a little bit later, but if I think of it as a wave, I can say, okay, it does what it does. If I think of it as a particle, it's a little troubling because you imagine a beam of light made up of millions of little BBs or photons. These photons are identical, and so let's see, I have 50 photons coming here. Some of them bounce off and some refract, and this gets really bizarre because how does a particular photon know which path it's supposed to take? And this bothers physicists quite a bit. if we treat things the same, they should behave the same. If I drop 10 rocks off of a building, I expect the 10 rocks to do the exact same thing. But if I shoot 50 photons, some of them bounce off and some pass through, and that's very troubling. That a photon would know, okay, I have to bounce off because my friend, the other photon, is going to refract. And again, this gets into this really strange idea known as quantum electrodynamics. Now, back to our topic that we need to know. There's something called internal reflection. Here's a really cool picture, and this is a demo I normally do in class, but obviously I'm doing this as a video, so it's tough to do. Here is a soda bottle filled with water, and a hole's been poked in the side, and we're shooting a laser beam through the water. The laser beam is actually going to follow the water stream. The light is going to hit the boundary between water and air, and it's actually, rather than passing through, it actually internally reflects. So the surface of the water into the air actually acts like a mirror. So you can see the beam is trying to get out, but it's hitting the boundary and bouncing off over and over again. So the laser is trapped inside this material. And it only happens under very unique conditions. So it doesn't happen all the time. You have to have a very particular setup with angles and different materials so the light is trapped. This is known as internal reflection. It's the basis behind fiber optics. This is a demo I do, and this is a little bit more clearer to see. We shoot again a laser beam within this beam and within this material. This glass must have an index of refraction that does not allow the light to pass through. Instead, the light is actually trapped inside, and every time it tries to get out, it's internally reflected. This is the basis again behind fiber optics. Fiber optics, of course, is used for endoscopes. Here we're looking down at somebody's lungs, so this is kind of a handy thing. You can actually put a small fiber optic material with a camera and carry light back to the doctor so you can actually look through the camera. And the key thing is the camera lens can be bent, so you can go into various areas to explore. Here are the fiber optic cables in detail. And again, I said that in class, a lot of data is carried by fiber optics as opposed to traditional copper wire. Here's a bizarre artwork dress made out of fiber optics. They plug it in and you have fiber optic material. I don't recommend wearing that dress, however. Now, internal reflection has to obey the laws we talked about before. So if light is going to reflect, it's going to reflect at the angle of incidence, angle of refraction. And how we figure out when it's going to do this versus refracting is, again, using Snell's law. Whenever you do a Snell's law and you do it correctly and you get an error message on your calculator, it means the light actually doesn't reflect, it doesn't refract, it actually reflects. So if you're doing a calculation with Snell's and your TI 83 or 84 gives you an error message for angle B, then you know you actually have internal reflection versus refraction, and it will reflect at the angles given by the law of reflection. So for example, and this only happens when we go from something that's very dense into something that's very low density. So internal reflection will only occur when n sub A is greater than n sub B. It will never happen the other way. Okay? Now, in this case, we're bringing light in from diamond at a very high angle, theta equals 75. So there's my theta A, here's my NA, and we're going into an NB that's much, much less. And what happens, and you'll have to do this, but if you do the calculation using Snell's law, saying NA sine theta A equals NB sine theta B, and again, just make sure that you're in degree mode in your calculator. When you solve for theta B, so you have to do the algebra and take the inverse sine of a big mess, you'll get an error message. And that means that rather than light passing through and bending, in this case it would bend away from the normal, it doesn't actually do that. It actually reflects right off at the exact same angle, so it comes out at 75 degrees. And again, engineers can design the material so it actually carries light information in light beams to actually internal reflect, so the light will be trapped. Now, we don't use diamond and water. It's usually a glass material or some sort of polymer that carries the material. This is going through and showing you that if I have 3 different light rays coming in here. If I send a light ray in on angle 1, so the angle is relatively shallow, relatively small angle, and again from a high index to a low index, this is the only condition we'll get the internal reflection and error message. In pathway 1, what typically happens is the light goes in, light comes out at an angle, and again, this is my theta 1, and here's my theta r for that case for 1. So angle of incidence 1, angle of refraction 1. Again, the angle is typical refraction, so this is regular old refraction. There is a very particular angle shown here as theta 2. This theta 2 is what we call the critical angle. If I send it in exactly at the perfect angle, and you can calculate this, and I'll show you in just a second how to calculate this, but if the light comes in exactly at the critical angle, then the light will actually go out along the boundary. So in this case, theta 2 equals theta critical. And that means the theta r will equal, well, if you remember, it's always relative to the normal line, so this angle would actually be 90 degrees. And finally, in theta 3, it's the example I just showed you. If I send the light in at a very high angle, you'll get an error message on your calculator, and you'll have the light come out at the angle of incidence. So it'll come out 3, this will be 2, and this will be pathway 1. So I'm trying to show you that in the first case, theta 1 is going to refract. The second case, we're actually at the critical angle. It comes out along the boundary. And if we exceeded the critical angle, then we're going to get light reflecting, like we just saw in the example a moment ago. In class, I usually do a demo. I shoot a laser beam down from air, I shoot light down from air into an unknown yellow liquid, usually water with food coloring in it. We'll actually get reflection off of the boundary. We'll get refraction in. Here's a mirror down here. You got reflection and refraction. It's kind of the picture we showed before, and I'll show you that demo in class. And there's a refraction homework that I believe is online, and there's a refraction packet, actually. It's online. So if you do the packet using Snell's law, you will need a protractor and ruler. If you need to get one from class, go ahead and do that, and you can do the calculations for refraction. And there's actually a pufferfish demo. Okay, we'll stop there for that video.